In the name of God, the most gracious, the most merciful, we begin today's episode about the differential relay. In American references, it is called the percentage differential relay, and it is also known as the low impedance differential relay. These relays have undergone several modifications to the simplified concept of the differential relay that was explained earlier. We will present an innovative idea through the use of what is called the restraining coil. So, what does this modification add? And how does it solve practical problems arising from the natural difference between the incoming and outgoing currents on the path? Protected element? Stay with us. Inspiring the renaissance of our nation. Initially, the differential relay used only the operating coil, the main coil shown here. A new restraining coil has been added to prevent incorrect operation. The differential relay now handles several currents. The differential current, I1, I2, also known as the operating current, flows through the operating coil. The torque from this current faces a counteracting restraining torque. This restraining torque comes from two cyclist currents, each the sum of incoming and outgoing currents divided by 2, called the balanced current. As current increases, resistance increases proportionally, so the restraining torque increases with the restraining current. If operating torque exceeds restraining torque, the relay trips. Otherwise, it does not. The term torque comes from the disk in old electromechanical relays. The restraining torque comes from two currents known as the balanced current. As current increases, resistance rises proportionally. If the operating torque surpasses the restraining torque, the differential relay trips. Torque refers to the disk torque in old electromechanical relays, but is used figuratively in modern relays. This topic involves competition, where one torque's dominance prompts the relay to trip or close. The operating torque increases with the operating current. If it surpasses the restraining torque, the differential relay issues a trip decision. Conversely, if the restraining torque is stronger, the relay remains inactive. Torque originates from the disk torque in old electromechanical relays, but is now used figuratively in modern relays. Typically, the coil has fewer turns than the operating coil. This topic involves competition between torques, prompting the relay to trip or stay open. The restraining coil, also known as the biased coil, prevents incorrect operation of the differential relay by resisting it. However, the term torque is still used even in modern relays in its figurative sense rather than its mechanical physics sense. Typically, the number of turns in the coil is less than the number of turns in the operating coil. Notice that this topic falls into the realm of competition, where one torque is stronger than the other, prompting the relay to make a decision to trip or close. The restraining coil, also known as the biased coil, prevents incorrect operation of the differential relay by resisting its activation. It is biased against the relay operating, balancing operating torque, and restraining torque. A slight difference in incoming and outgoing currents won't trigger the relay. For example, with incoming current at 5 amperes and outgoing at 4.5 amperes, the operating torque is 0.5 amperes, and the restraining torque is 4.7 amperes. Thus, the relay remains stable as the restraining current exceeds the operating current. Similarly, if this difference arises due to the asymmetry of the current transformer, the example clarifies the concept. For instance, if we assume that the incoming current is 5 amperes and the outgoing current is 4.5 amperes, what are the values of the operating torque and the restraining torque? The operating torque is 0.5 amperes, while the restraining torque is 4.7 amperes. Despite the 0.5 amperes difference, the device stays stable and doesn't operate because the restraining current is greater. If a fault occurs, a big difference arises, like 20 amperes incoming and 1 ampere outgoing. The operating torque is 19 amperes and the restraining torque is 10.5 amperes. Since the operating current is greater, the relay trips to disconnect the faulty part. This raises a question. Is every slight current increase a fault for the relay to trip? This is required. If a fault occurs in the protected area, a difference arises in currents. The operating torque is 19 amperes, and the restraining torque is 10.5 amperes. The relay trips to disconnect the fault. Is every slight current increase a fault? No. The operating current must exceed a certain percentage of the restraining current for the relay to trip. The relay trips if operating current is greater than K times the restraining current. If the operating current exceeds a certain percentage of the restraining current, the relay trips. Must the operating current exceed a certain percentage of the restraining current for the relay to trip? Yes, for percentage differential protection. The relay trips if the operating current is greater than K times the restraining current. Of course not, as the operating current must exceed a certain percentage of the restraining current for the differential relay to issue a trip decision. This is why this protection is called percentage differential protection. This percentage is denoted by the symbol K, or may be referred to as slope. The differential relay should issue a trip signal if the value of the operating current is greater than K times the restraining current. This method, representing the relationship between the operating current and the restraint current, shows the percentage of errors caused by the asymmetry between the incoming and outgoing currents. The concept of slope comes from delta y over delta x, where delta y represents the operating current while delta x represents the restraint current. Thus, the value of K equals I operating divided by I restraint. For example, if the slope value is 10%, this means that the operating current must exceed 10% of the restraint current for the relay to issue a trip signal. If the slope value is 10%, the operating current must be over 10% of the restraining current to trip or disconnect. If in the pink area above the curve, the relay trips. If below, it stays stable. A lower slope means more sensitivity, needing less current difference to disconnect. This method can be 10%, 20%, or 40%. If the operating current is in the pink area at the red point above the curve, the relay should trip. If below the curve at the black point, the relay remains stable. A lower slope means more sensitivity, requiring a smaller current difference to trip. Lower slopes also mean smaller expected errors, like CT asymmetry. The differential curve shows a slight rise above zero for safety, hence called biased differential protection. It helps overcome friction in traditional devices. Typically, the differential current setting is very small, from 0.1 to 0.5A, known as the minimum differential pickup current. This diagram shows erroneous current differences during normal load or external fault. From another perspective, we can say that the lower the slope, the smaller the expected errors, which are usually taken into account, such as the asymmetry of the CTs. Notice in this differential curve that there is a slight rise above zero for the operating current at the start of operation, which is necessary as a safety margin against incorrect operation. Therefore, this protection is called biased differential protection, as it also helps overcome friction in traditional devices. Typically, the differential current setting is adjusted to very small values, with a setting range from 0.1 to 0.5A, which is referred to as the minimum differential pickup current. This diagram shows the values of the erroneous current differences that appeared or arose during the passage of the normal load current or during the limits of an external fault. Notice how it was chosen to be higher than the sum of these currents to avoid incorrect operation, as if we have slightly raised the curve upwards. This is the current curve that represents the error resulting from. On the other hand, this curve represents the percentage of error from, and this curve represents the error resulting from the reading itself and the sum of these errors. The total false current is represented by the total false current. The relay operating curve must be above the total false current curve. This point is the minimum differential pickup current. To ensure the relay trips for real faults, let's revisit the example from the last episode. Assume the slope setting is 25%, with a normal current of 100 amperes and an error of plus 10%, 4.5 amperes flow in CT1 secondary, and 5.5 amperes in CT2 secondary. Their sum in the operating coil equals 1 ampere. To ensure the relay trips for real faults and ignores normal small current mismatches, assume slope setting is 25%. Normally, with 100 amperes and plus 10% error, 4.5 amperes flow in CT1 secondary, and 5.5 amperes flow in CT2 secondary. Their directional sum in the coil equals 1 ampere. In CT2 secondary, the directional sum in the operating coil will equal approximately 1 ampere. And this is the value of the differential current because it's the difference between them. As for the restraining current, it will be 4.5 plus 5.5 divided by 2, which equals 5 amperes. Here we strongly warn against performing directional summation when calculating the restraining current. Whether the current is upward, downward, to the right, or to the left, we take the positive value. The I restraint equals the absolute value of I1 plus the absolute value of I2 divided by 2. And it's not a directional summation, but rather an algebraic sum. On the other hand, the differential current is the absolute value of the directional sum between them, meaning I differential equals the absolute value of I1 plus I2. The result remains unchanged, and the negative sign shouldn't confuse engineers. During a fault, the differential current is the absolute value of the directional sum of the currents, while the bias current is the sum of their absolute values, divided by 2. The differential, it doesn't differ from that. If we have 3 sources at the moment of a fault in feeder protection, for example, the differential current will be the absolute value of the directional sum of the 3 currents together, while the bias current will be the absolute value of the first current plus the absolute value of the second current plus the absolute value of the third current, all summed up and divided by 2. Now let's return to the previous example again. We said the differential current, Dr. 1 ampere, and the restraint current, Dr. 5 amperes. The ratio of the differential current to the restraint current is 1 over 5, R for 0.2. We use 0.2 for the slope, Dr. 20%. Since 20% is less than the slope setting of 25%, no trip signal will be issued. Measured slope 20%, setting 25%, no trip signal, stable. 1000A external fault, differential current is 10 amperes from 55 minus 45, restraint current is 50 amperes from 55 plus 45, 2. In the same idea, if there is an external fault with a value of 1000 amperes, the differential current will be 10 amperes, which results from 55 minus 45. As for the restraint current, its value will be 50 amperes, which results from 55 plus 45 divided by 2. Ratio 0.2 gives 20%. The differential to restraint current ratio is 0.2, 1050. Since 20% is below the 25% slope setting, no trip signal is issued, remaining stable. For an internal fault of 1000A from one source, CT1 reads 45A. The differential current is 45A, as there's no opposing current. The restraint current is 22.5A, 45 to 2. The differential to restraint ratio is 2, 45 to 22.5. Since 200% exceeds the full 25% slope setting, a trip signal is issued. The value of CT1 will be 45 amperes, while the value of the differential current will be the same because there is no current from the other side to cancel it out or oppose it in direction. As for the restraint current, it will be this current divided by 2, so 45 divided by 2 equals 22.5. Differential restraint current ratio is 2. 100% exceeds 25%, trip signal needed. Internal fault, CT1 45A, CT2 55A, sum 100A. And it equals 200%. Since 200% is higher than the slope value, which is 25%, a trip signal must definitely be issued here. If an internal fault occurs and is fed from 2 sources, the CT1 secondary current will be 45 amperes, while the CT2 secondary current will be 55 amperes. In this case, both currents will flow to the differential relay from the bottom to the top. So their directional sum will be 45 plus 55, which equals 100 amperes, representing the value of the differential current. As for the restraint current, divided by 2D100 divided by 2 and equals 50 amperes. As for the differential current percentage of the restraint current, it is 100 out of 50 and equals 2. Then we multiply this 2 by 100% until we get the measured slope, which equals 200%. 200% is higher than the slope setting of 25%, so the relay will trip the circuit breaker. The relay trips if the ratio is above this line, called the trip area. No trip signal if the ratio is below this line, called the restraint area. An internal fault raises both differential and restraint currents simultaneously. Any differential point over restraint moves along this curve from the restraint area. From the above, we conclude that an internal fault will raise the values of both the differential current and the restraint current simultaneously. Therefore, we can imagine that any point of differential over any restraint will move along this curve from the restraint area. We must not forget to raise the curve a bit to avoid the incorrect operation it causes, especially in the case of transformers that are not connected to loads. Therefore, we raise the curve so that it is above the sum, as shown in this image. Notice here that the value of the French current or racing current, it can be expressed in amperes or as a percentage or tap settings. 0.3 tap setting will be detailed later. Notice, something 3 for differential current stayed constant as restraining current rose from 0 to 1, like a flat line. Not all relays have this line. Some rise after 0.3. Assume a fault due to high resistance with a small difference in currents. Incoming was 320A, outgoing 304A, with a CT ratio of 400 to 5. Will it detect the fault? Convert currents from primary to secondary. If 400A gives 5A, how much will 300 320A give? After the relay, we found this line, but in some others, the line rises directly after point 3. Now let's assume that a fault occurred due to high resistance within the protected area, where the difference between the incoming and outgoing currents was not significant. The incoming current was 320 amperes, while the outgoing current was 304 amperes, and the CT ratio at the terminals of the protected element was 400 to 5. Regarding the differential relay with a 10% slope, will it detect this fault? First, convert the incoming and outgoing currents from primary to CT secondary. If 400A gives 5A in the secondary, what about 320A? For 320A, it gives 4A in the secondary. Similarly, 304A gives 3.8A. Now calculate the differential and strain currents. The differential current is the incoming minus outgoing. 4, 3.8, 0.2A. Alternatively, 4 at 0 degrees plus 3.8 at 180 degrees equals 0.2A. Both methods yield the same result. The differential current must be positive, as it's an absolute value. The straining current is the incoming plus outgoing divided by 2, 4 plus 3.8, 2, 3.9A. Thus, the differential current is 0.2A. The differential current, or operating current, is the incoming current minus the outgoing current. 4 minus 3.8 equals 0.2 amperes. We can also say that the differential current is 4 at an angle of 0 degrees plus 3.8 at an angle of 180 degrees, which equals 0.2. Both methods should yield the same result, of course. The most important thing for me is that the value of the differential current is positive, not negative, because we previously said it's a difference, not a subtraction, meaning we take the absolute value of both. As for the straining current or bias current, it is the incoming current plus the outgoing current divided by 2. So 4 amperes plus 3.8 amperes divided by 2 equals 7.8 divided by 2, which equals 3.9 amperes. Therefore, the value of the differential current is 0.2, and it equals 3.9 amperes. So, the value of the differential current is 0.2. While the value is 3.9 amperes, they are under the slope. If the point is in this area, the device won't detect the fault, a problem. The point should be in the trip area for a decision. The differential current must exceed 10% of the restraint current for a trip. 10% of the restraint current is 0.39 amperes. Thus, it must exceed 0.39 amperes for a trip signal. In high-level external faults, a CT may saturate, or until the relay dismisses. This means that the differential current must exceed 10% of the restraint current for a trip decision to be issued, and 10% of the restraint current is how much? 0.39 amperes. This means that the differential current must exceed 0.39 amperes for the relay to issue a trip signal. In the case of high-level external faults, there is a possibility that one of the CTs, A, enter saturation. This problem can cause incorrect operation of the relay, because the relay will see current from one of the CTs, but not from the other side when the CT is saturated. Therefore, in such cases, we have to adjust the curve by adding a slope 2 or K2 slope that is higher than slope 1. With this step, we have reduced the sensitivity of the relay to ensure its stability during external faults. The term stability is related to unit protection, which protects one unit and no other. This protection should be unaffected by external faults, as backup protection handles that. It should also resist through fault current. Even, this adjustment raises the slope 2 curve higher if the value rises above the differential current, a momentary condition. The red point marking the transition from slope 1 to slope 2 varies by manufacturer, being either predefined or adjustable. With this adjustment, we have raised the slope 2 curve to be higher in case the value increases significantly compared to the differential current, which is a momentary condition. As for this red point, that represents the transition from slope 1 to slope 2, it is called, and it varies from manufacturer to manufacturer, as it can be predefined in one or can be set for it. Low current results in low restraint current, increasing sensitivity. High external fault current increases restraint, reducing sensitivity and slope, preventing errors. Internal faults raising restraint, decrease sensitivity, needing higher differential current. Internal faults trip relay. Calculate expected fault current to stay within limits. If it arises due to external faults, the restraint current will be large, and therefore the relay should operate with less sensitivity and at a higher slope. This way, the relay is less prone to any incorrect operation while still remaining sensitive at low current levels. Someone might ask, what if an internal fault occurs that significantly raises the value of the restraint current? Therefore, an increase in the strain current will reduce the sensitivity of the relay and raise the value of the differential current required to operate the relay. Here, we say that in the case of internal faults, the value of the differential current will be very high, and no matter how low the sensitivity of the relay is, it will inevitably trip. Additionally, we need to calculate the expected fault current in advance and then plot it on the curve to ensure that it does not exceed any limits. On the relay, to distinguish between fault current and non-fault current, now notice in this diagram how we raise the slope of the differential curve so that it is above the saturation area of the CTs to prevent any incorrect operation. The area A, as shown in the image, represents the healthy state, which represents the sum of the expected differential current errors due to the inaccuracy of the statism or the lack of complete representation between them or the errors resulting from the tab changes. As for area B, it represents the area of internal faults, where the ideal case of faults is usually represented by a line at a 45-degree angle, meaning that the ratio between I operating and I restrained equals 1. Due to differences in currents during internal faults, the ratio may be less than 1. Modern relays with saturation detectors quickly detect saturation to ensure stability. They rely on CTs to briefly transform current before it changes. In external faults, differential current should be 0, but a small constant value exists. In internal faults, both values rise together. A time delay between these rises is crucial. It contains saturation detectors, which detect saturation conditions and ensure the stability of the differential relay. Its operation relies on the CT transforming the current briefly before the current shape changes. In an external fault, the differential current should be 0, but practically, a small value remains constant during the external fault. In an internal fault, both values rise together. A time delay between the rise of values is crucial. There is a small value that should not change during an external fault, while noticing a sharp increase. In an internal fault, both values rise together. A time delay between their rises is crucial. Value increase during external faults shows CT saturation. See the diagram analyzing point XY's path, where X is I restrain and Y is I operating during an external fault without CT saturation. Compare this with an external fault causing CT saturation and observe the difference. And the high value of the during external faults, this is the strongest evidence of the CT entering saturation. Notice in this diagram the analysis of the movement path of point XY, where X is the I restrain and Y is the I operating at the moment of an external fault without any CT saturation. Now, if an external fault causes one of the CTs to enter saturation, compare the difference between them. Initially, in the case of a fault, the point will be around the dashed line at a 45-degree angle, meaning it could be slightly above or below it. This dashed line is referred to as if a fault occurs that does not lead to the current transformer entering saturation, the point will move to position number 1. In saturation, the point moves from 0 to 10, indicating relay stability. A fault shifts it from 0 to 1, then jumps to 3, then to number 2, 3, 4, 5, and so on horizontally, with low value. It returns from number 6, 7, 8, 9, 10. This indicates the stability of the relay. However, if an external fault causes the current transformer to enter saturation, the point will move from 0 to position number 1, then move to number 2 horizontally, and suddenly jump up to position number 3. Observe how I restrain rose as I operating current remained low, and then I operating current suddenly rose. It returned to 0 due to fault currents when the breaker opened, making both I restrain and I operating current 0. If the current transformer enters saturation, the point will move from 0 to position number 1, then move to number 2 horizontally. Notice how the value of I restrain initially increased while the I operating current remained low at a certain moment in time, and then the I operating current suddenly rose. At this point, it returned to 0 from 7 to 8, and so on, due to the fault currents when the circuit breaker opened, where both I restrain and I operating current became 0. Both will equal 0. In the case of detecting a saturation condition, the relay will take action by temporarily raising the value of the restraint current by multiplying it by a bias factor or applying a differential block at the moment of detection to prevent issuing a trip signal for 150 milliseconds to ensure the external short circuit has cleared. For 150 milliseconds to ensure that this external short circuit is gone. Fault clearing time is 100 millis with a 50 millis margin. Faster saturation detection improves relay stability. All differential relays agree on the differential current equation, but differ on the bias or strain current equation. Some use the equation where bias current equals I1 plus I2 with I1 as incoming and I2 as outgoing current, multiplied by a variable coefficient K. Previously, we assumed K at 2, but it can be 1 in some cases. Other relays calculate it as incoming plus outgoing, or as the vector difference of incoming and outgoing currents. However, they differ in the equation for calculating the bias current or the strain current. Some rely on the equation where the bias current equals the absolute value of I1 plus the absolute value of I2, where I1 is the incoming current, I2 is the outgoing current, multiplied by K, where K is a coefficient that varies from one relay to another. We used it in previous examples, assuming its value equals 2, and these cases are waiting on the microprocessor and the ERB relays. While the value in it equals 1, we can use the calculation equation in other relays, which states that it equals the absolute value of the incoming current plus the absolute value of the outgoing current minus. Or we can say that in other relays, it also equals the vector value of the incoming current minus the vector value of the outgoing current. You can take the highest value of the in-out current or the lowest value of the in-out current. Some relays use bias current as SQRT I12, I2, co-ST-at. Know each relay's I-bias calculation to test correctly. Notice this relay for busbar differential protection uses the first equation for I-bias. I-bias, Chern's I1 turn plus, I2 turn K, with K bar 1, I-bias, Chern, I1 turn plus, I2 can plus, I3 can, etc. Differential current, Chern, S-feeder currents. Stay tuned for upcoming episodes analyzing bus differential protection. See you soon, where I-bias equals the absolute value of I1 plus the absolute value of I2 over K, but we choose the value of K, which is equal to 1, where the value of at I-bias becomes the absolute value of the current of the first feeder plus the absolute value of the current of the second feeder plus the absolute value of the current of the third feeder, and so on. As for the equation for the differential current, we said it remains the same. It is the absolute value of the vector sum of the first feeder current plus the second feeder current plus the third feeder current, and so on. Stay tuned for the upcoming episodes, where we will analyze the operating characteristics of bus differential protection for several different relays. Be there, and we'll see you soon.